Okay, so welcome back. This is part 3 in our series on understanding electronics. And in the first couple of videos, we talked about some basic concepts with active devices like MOSFETs and how they work and how they are very similar to water valves and water pressure and water flow. And in the second video, we showed how to set up a LTSPICE simulation with a MOSFET and how to get the model and how to set it all up so that we can, in preparation for this video where we're going to actually run some simulations on some MOSFETs and see how they respond and check their operation versus their spec sheets and hopefully get a better understanding by actually doing it and trying it out. And then in our next video, or one of our next videos, we're going to actually do some bench testing of the same MOSFET with real-world scopes and voltage sources and see if it all matches our simulations. Okay, so in previous videos in this series, the first one we talked about some basic concepts surrounding electronics and tried to give a very simple analogy to electronics and what it really means because as you may know, if you've done any electronics work, there's a lot of equations and complicated graphs, and really at the core, it's not all that complicated. So if you get the basic understanding down, then it's a lot easier. You know, maybe you can make your own equations and you can figure your own stuff out instead of having to just, from memory, remember what you saw and not really understand it. So the first video in the series, we talked about the basic concepts. The second one, I showed how to configure this circuit here, which is a very, very simple LTSPICE circuit for the international rectifier MOSFET we chose. And I showed you, I went on eBay to show you what's available on eBay, the stuff you could buy if you want to later on put it on, do some bench testing, and also to simulate it in LTSPICE like we've got here, and showed you how to download the LTSPICE model for this and install it and get it set up so we can, compare what we simulate with the spec sheet for the actual device and then maybe even buy one and bench test it. So this is what we did in the previous video. We set up a very simple circuit where we've got this international rectifier F540N model, and we hooked it up with two voltage sources. And we've got a V1, which is a DC 10 volts I put in here. Connect that up to the gate, which is terminal 2. And then we've grounded the source, which is terminal 3. And terminal 1 is the drain, and we connected that directly across, and I put in a 12-volt source here. So we're going to start off with this one because it's very simple and very easy to understand. And it gives you a good idea about how this MOSFET responds to very simple inputs and outputs. So the other thing I did is I downloaded a spec sheet for this international rectifier IRF540N, which is a HEXFET power MOSFET, blah, blah, blah. It's got a whole bunch of stuff here. And what we want to do is first, and by the way, these spec sheets are very easily available. You just search on the model name of the device, and chances are you'll find a spec sheet for it on the internet. So this spec sheet, I've highlighted some of the important parts to it that you're going to want to check first off to make sure you're operating within the range and so you can understand better what it's doing. So VDSS, which is the maximum drain to source voltage that this thing can withstand, which is surprisingly 100 volts, all right? Which means I can apply between this drain and this source a maximum of 100 volts. So we're going to keep it way below that. We're going to keep it at 12 volts, but just so you know, that's what you can apply. I drain maximum is 33 amps. Again, very surprising. So that means that the current flowing through this circuit from drain to source to ground and back to this 12 volt, maximum of 33 amps. Okay, so you're going to want to make sure that you're below 100 volts across drain to source and that you're below 33 amps. All right. And we're way below. We're 12 volts, and we'll see the amps when we do the simulation. So again, here's ID, which is the continuous drain current. We just saw is 33 amps. And the maximum gate to source voltage you can apply is plus or minus 20 volts, okay? So this voltage can be no more than plus or minus 20 volts. And we've got 10 volts we're applying. So we're within the specs. So now if we scroll down, we can see the electrical characteristics with a junction temperature of 25C. I've highlighted the VGS, which is the gate threshold voltage. Now recall when we were dealing with the water valve, we said you need, in order to start opening this valve, you got to turn it about a half a turn before this actually starts opening. And there's a very similar concept with the MOSFET, where you have to get up to, you have to apply a few volts for this thing to even start turning on or allowing current to flow. And here it says there's a minimum of 2 up to 4 volts that have to be applied to the gate, between gate and ground, in order for this thing to start turning on. So now we know that in order to turn this thing on, we're going to have something like 2 to 4 volts to get this thing going, all right? So now we know where we are in general in applying this thing. So we're going to apply something more than 2 to 4 volts, and then that will cause the resistance of this device to change, which means if I apply 12 volts, the current will change. So we're going to be interested in seeing how this responds as we apply voltage, how that changes the resistance between the drain and the source, allowing more current to flow. Now keep in mind, I don't have anything else in the circuit here. So when I apply 12 volts from drain to ground, that's applying a full 12 volts at all times between drain to source to ground, all right? So I'm always going to be having 12 volts across here. And if, as I vary the gate voltage, if that results in a changing resistance between drain and source, kind of like varying the gate handle with the valve changes the drain to source resistance, that means I'm always going to have 12 volts measured across here. And what's going to change is the resistance, which means the current flow is going to change. So as I increase this gate voltage above about, we said 2 to 4 volts, this is going to turn on, and we're expecting that there's going to be very little, once this is on, there's going to be very little change in gate voltage to make this go totally on, which means you're going to have the maximum current flow. And it's probably going to be only varying this gate voltage by a volt or two, okay? And we're going to see that. So that's where we stand with our basic setup. So what we're going to do now is we're going to start varying these things and do a simulation to see what the results are. So the first thing I'd like to do is, we said that if you vary this gate voltage, then the drain to source resistance will change. The voltage will remain at 12 volts, but the resistance will change, and therefore we can expect the current to change between drain to source to ground, because you got a varying resistance and a constant voltage. So how would we do that? Ideally, I would like to take the V in and vary it across a range. We said it's got to be, maybe 2 to 4 volts to turn this on. So I'd like to have the V in automatically go from 0 to, say, 5 volts, and just watch the current flowing from drain to source to see what effect that actually has in the real world. And the wonderful thing about a software simulator is you can do that very easily. So what I've done is I have set up what's called a DC sweep. So I'm going to the simulate, edit simulation command, and I've got a DC sweep. And all that does is it varies. You specify what voltage you want it to vary, and this is going to vary this source or gain voltage. And I've specified V1 is going to sweep. It's going to be a linear sweep. and it's going to start with a value of 3 volts, and it's going to go up to 5 volts. Remember we said 2 to 4 volts it's going to require. I know that this thing is a little bit higher than 2 volts. It's closer to 3 is the minimum because I've already tested it. So just to make it look nice, I'm going to vary it between 3 and 5 volts going into this gate, increments of 10 milliamps, and see what the output, what the current going through drain to source to ground is going to be. Okay, so I've already done that, and here is the resulting graph. So basically all you do is you take that simulation, you hit the running guy, and it runs the simulation and gives you that graph. I tweaked it a little bit. You can use the, see this, you hover down here on the graph with this ruler, and then you right click and you can select the minimum, maximum, and tick marks, however you want. So I've already done that just to make it a little bit easier to see. And you can see here is down in the bottom left, I've got 3 volts applied to the gate. And you can see the current flowing from this 12 volt source through the drain to source to ground is 0. And it's 0 amps all the way up to a little over 3.6 volts. So they said 2 to 4. It's actually 3.6, at least in this model. To the extent you can trust this model, it's 3.4 or 3.6 volts required to just get this turned on. Okay, just like this water valve, you got to turn it a little bit. In this case, you got to turn it to 3.6 volts just to get that thing to start opening. So after 3.6 volts, as I go to 3.8 to 4, you can see I'm getting up around 6 amps flowing from drain to source, okay? So again, it's constant 12 volts, so the only thing that's varying is the resistance between drain and source. And you can see it gets more and more and more, and we said the maximum, the limit of the current that can flow from drain to source is 33 amps. So to get 33 amps, I've got to be up around, you can see down the bottom right, I've got 5 volts applied, and it's almost up to 30 amps. So somewhere around 5 volts applied in this gate with no other resistance or impedance here in the circuit will cause the maximum rated current to flow from drain to source if I've got a 12 volt source and I've got this IRF 540. So you can see that between 3.6 and 5 volts, which is only 1.4 volts variation in the gate voltage, I can go from totally closed to having 30 amps flowing in only a variation of 1.4 volts, all right? So like I said, here we took a whole lot of pressure and energy to open this. With the MOSFET, it's like you just tweak this a little bit, you turn it a tiny fraction of a turn, and this thing suddenly jumps open, okay? So now we've got a good feeling for how this guy responds, and it's basically, I've got a constant voltage, it basically varies the resistance between drain and source and causes current to flow. So now the next thing I'm curious about, well, what does that result in terms of actual ohms between drain and source? All right. So what I've done is I simulated different voltages, and here's my V in, which is basically this gate voltage. I started from 3.5 volts, which is down here somewhere, and you can see that it's totally off, which means an infinite impedance between drain and source. Okay. And I cranked it up to 5 volts in steps of 1/10 of a volt. And I measured how much current is flowing between drain and source. And then I calculated the resistance of drain and source on each of those steps. And you can see I start out at 3.5, there's 0 current, which means infinite resistance. If I go to 3.6, now I've got 618 ohms of resistance between drain and source. And if I go up to 3.8, I've only got 6 now. So it's gone from a few tenths of a volt, it's gone from 600 ohms down to 6 ohms. And then 3.9 is 3.6 ohms. And then 4 volts is 2 ohms. So you can see it's flattening out to something just under 1 ohm as I crank it up to 5 volts. So you can see there's a very sensitive and wide variation in resistance between drain and source as I vary this input voltage. And that's basically the MOSFET. That's basically how it works. You're basically changing the input voltage, which varies the drain to source resistance, which causes current to flow, very much like this guy, a very, very, very sensitive version of this guy, okay? Okay, so now we know that in a very simple perspective, with a MOSFET, with this particular MOSFET, when you change the input voltage to the gate from around 2 to actually more like 3.6 and above, it changes the resistance between the drain and the source. And it starts out at infinite and goes down to very low, less than 0.1, okay? So positive voltage changes the resistance. Now, so what happens if I apply like a sine wave that goes to negative voltage? What does it do? What if I want to amplify a sine wave that goes from 0 to plus 10 and then down to minus 10 and then plus 10? What's this thing going to do? When it goes negative, it's going to shut down and I can't amplify my sine wave. So what's going to happen? Well, what I've done here is I've tweaked our circuit just a little bit. Instead of a DC, I've added a sine wave with a peak amplitude of 4 volts. Now remember, we previously said this guy needs about 3.6 to turn on, so I'm just above 4 volts, and I've got a 100 hertz sine wave. And I added a 1 ohm resistor here just to see what the output is going to be as I vary this, and see what's going to happen to the sine wave that I want to amplify, see what's going to happen on the output to the sine wave. So I've already done that again, and here's the results. Now this yellow sine wave is this input, and you can see it goes up to, here's 3.6, it goes up to 4 volts peak, and then goes down to minus 4 volts, then up and back and forth. So that's this gate voltage is varying, as we said, 0 to plus or minus 4 volts. Now, what I've done here is I have measured in blue the voltage across this R1, 1 ohm, okay? And I want to see what's going to happen to the output voltage as I vary the input voltage. And you can see, hey, wait a minute, my sine wave, as we kind of expected, when it goes negative on the input, the output goes to 0. And when it gets above, you can see here's 3.6 here on the left. When it gets above 3.6, you can see, hey, it starts to conduct. And now you're starting to get an output. And then when it gets down below 3.6, it shuts off again. So it's making sense. It turns on at 3.6, and it doesn't allow negative voltages like a negative sine wave to it shuts down anything below 3.6, even if, and especially if it's negative. So now we're going to have to figure out, how do we get this so that the input never goes negative? I've got a negative sine wave, but I want to kind of shift it up so this negative 4 down here is maybe greater than 0, so that I can take this sine wave and amplify it to make it into a positive sine wave on the output. Well, that's going to take what's called biasing. And all that means is I take this plus and minus 4 volt sine wave and I add a DC value to it to shift it up so that the minus 4 input is actually becomes positive into the gate. All right? So we're going to talk next about biasing the input so you can amplify this input sine wave and have it amplify on the output. So I hope that helps. Take care and have a really good day. Thanks.